We have reached the definition of the definite integral. Dun, da, da, da. Okay, so this is just like with derivatives, for example, we have our mathematical definition, and then we also have a what does this represent? Uh, Essentially definition. So, like when we talk about what is a derivative, we'll usually what we answer is it's the slope of the line that's tangent to a curve. But our definition is the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so we've got our definition, and then we have the what does it mean. So here we have the definition first, and that's this first line. Okay, so the definite integral of a function f on an interval from a closed interval from a to b is written like this. It's the integral. When we read it, we say the integral from from a to b. Okay, and then a is on the left, b is on the right, the order matters, of f of x dx. So again, this is the integral from a to b of f of x dx. Okay, and that's equal to the limit as n approaches infinity of the sum from 1 to n of f of x sub I times delta x, or times delta xi, again, doesn't matter, where delta x is equal to b minus a over n, and x sub I equals a plus I delta x. Okay, so all of the stuff that we just talked about at the end of the last video, this is the definition of the definite integral. Okay, in words, it's the sum of the areas. So this is the area of an infinite number of rectangles. Okay, all of those rectangles being infinitely smaller, infinitely thin. So each of the subintervals approaches a width of 0. Okay, now what does it represent? It represents the area under a positive curve f of x on that closed interval. Again, we will get to what happens if part of that integral is negative, but for now, this integral does represent area if the curve is positive. Okay, so let's look at this example. It says write a definite integral to represent the area of the shaded area. Okay, or should be area of the shaded region, so we don't use the word area twice. Okay, and we can do this a couple of different ways. We do need some kind of equation to represent this. We can do it as one function. So this function appears to be a vertical flip of the absolute value of x shifted up 4. So we could say f of x equals 4 minus the absolute value of x. We could do it that way, and then we could integrate it. So we could say area is equal to the integral from 1, 2, 3, negative 4 to positive 4 of 4 minus the absolute value of x. And then we do have to have dx behind it. Okay. Or actually a couple options here. We also could do this as two functions. We could do the area on the left part. Let me switch colors. So we could do the area of this part and the area of this part separately. So we could say that's also equal to the integral from negative 4 to 0. And then this line would be y equals x plus 4. And then times dx plus the area of this piece from 0 to 4 of, and then that would be 4 minus x dx. Okay. Or we could also pick one or the other sides, do the area of that, and then double it, because again, it's a triangle. So we could say 2 times the integral from 0 to 4 of 4 minus x dx. Okay. Either way, all three of these, this one, and this one, all give us the area of that orange region. Just a note here, I'm not super careful about putting parentheses around the integrand, because the integrand is the part on the inside, kind of like a radicand is the part under a radical. Okay, because this is called a summa, Latin. Okay, it's this big S shape, similar to a sigma, so you can see how they're related. So this summa here and the dx at the end essentially act as bookends. You cannot have, this is a big deal for notation, you cannot have this without this. If you have an integral, you have to have dx, or whatever the variable is, dt, dy, at the end, okay? Must be there. Now, most of the time when you see these written, there will be parentheses appropriately on the inside, grouping all of that together. But again, I'm not super consistent with that, and it's really not a big deal as long as you have both of those pieces. Okay. So let's look at one more example here, and it's got a few different parts. Oh, sorry. Before we try this, we need to answer the question of what happens if part of the function is negative, because there will be some negative pieces down here. And I apologize, I forgot to add this in, so I'm just going to come down here. If part of f of x on the interval from a to b is below the x-axis, okay, then the integral from a to b of f of x dx does not find area, it finds net area. Okay, net area meaning it takes the area that is above and it subtracts the area that is below. So if I had something, let's say I've got something like this. So let's call this A. I'm going to call this point B. Let's call this point C. Okay, so if I integrate, we'll call this function f. If I integrate from A to C on this function, it's going to take the area above the x-axis and it's going to subtract the area below. Oops, W there. Okay, so we find net area. Anything that is below the x-axis, okay, that is below the x-axis is area that gets subtracted. Okay, the reason this happens is if you think about our definition comes from an infinite number of rectangles and the areas of those rectangles added together. But remember, each rectangle has a height that is f of xi. In other words, it's the y coordinate of each sample point. So if I have an infinite number of rectangles, but I'm looking at the rectangles that are inside this part, again, they'll be infinitely thin here, but all of them, the f of xi values are going to be less than 0. So when I do the height, the quote height of the function at each of these points, I'm going to get a negative value multiplied by the horizontal width, which is still delta x. And so I have what looks like a negative area. Let me stress, area cannot be negative, but area can be subtracted. Okay? All right, let's go back to these examples. So for this first one, here's our graph of f of x, okay? And it's piecewise function. We've got quarter circle, trapezoid, triangle, or we can break this into triangles and rectangles. Okay, so the first part says the integral from -4 to 0. Oh, and I would suggest maybe pause it here and give them a try and then resume and see if we got the same thing. Okay, so integral from -4 to 0 of negative f of x. Okay, well, let's think about what that function looks like. Negative f of x would be a vertical flip of this function. So essentially, I would be looking at, so 1, 2, from -4, which is right here, going to reflect that point. I would have a quarter circle here, and then a line segment here. So if I integrate from -4 to 0 of negative f of x, I'm looking at this area and this area, and because those are below the x-axis, I will be subtracting both of those. So this is going to be the opposite of, and so this is a circle with a radius of 2, so the full circle would have an area of 4 pi, but we have a quarter of that, so it's just pi, and then minus this triangle is 2 by 1, so 1/2 times 2 times 1 is 1. So negative pi minus 1 is the value of this definite integral. Okay? And if you want to sketch graphs, that's great. The second one, we're doing the integral from 2 to 6 of the absolute value of f of x. So I need to see how that absolute value transforms this function. We're going from, let me switch colors again, do orange change here. So we're going from 2 to 6, 4, 6, okay? Absolute value takes anything negative and it makes it positive. So this piece right here gets flipped up to here, reflecting it. And so now I'm looking at the area of a trapezoid plus a triangle, or we could do a square plus a half of a square with a triangle. Doesn't really matter. Geometrically, however you want to piece it together is fine. So if I do a trapezoid, I've got 2 plus 1 over 2, which is 3 halves, times height of 1, so 3 halves. Or again, 1.5 squares, plus, and then this is a 2 by 2, 1/2 times 2 times 2 is 2. So 3 halves plus 2, we can add that together, and we get 3 halves plus 4 halves is 7 halves, or 3.5. Okay. All right, for this next one, f of x plus 2. When we add 2 on the inside of the function, that takes the function and it shifts it horizontally because we're adding 2 on the inside. That means we are moving to the left. Okay, and I'm actually going to kind of resketch my function here instead of continuing to draw on the same one so that it looks okay when I print it. Okay. And we're going from -2 to 1, so I care about from this point here to this point here. Okay, and I'm shifting 2 to the left. Let's see, height of 1. Okay, so this x-intercept comes over here to -4, and then has a slope of 1/2 up to this point, and then it's just a horizontal line. And we are going to 1. Okay, yeah. So we are looking at oh, we only need to go from -2 to 1 though. Okay, so this is what the graph looks like. I just shifted that part over. The integral from -2 to 1 would be the area of this piece right here, which is 3 by 1. So that's going to be a 3. Okay, now on this one, just a suggestion, instead of shifting the graph 2 units to the left, we could also take our these are called limits, the a and b values are limits, and shift them 2 to the right. So if go back to the original graph, the original function here, get rid of these circles. The integral from -2 to 1 of the shifted graph is the same thing as the integral from 0 to 3. So this right here on the original graph. Okay, so instead of shifting 2 to the left, we could say that's the same thing as, and then shift the units or the limits 2 to the right. So it'd be 0 to 3 of the original f of x dx. Now you don't have to do that. This is not a hard one to move, but just keep in mind that that does work. Okay. All right. Then for the last one, we have the function f of x plus 2. Okay, so that's a vertical shift of this function, and we're integrating from 0 to 3. So again, I'm going to sketch. And so from 0 to 3, I just care about, so at 1 over to 3. Okay, so I'm looking at this piece right here, and I'm shifting it up 2. So it just looks like that. Okay, so we actually have a rectangle that is a 3 by 3, or a square, 3 by 3, which gives us an area of 9. Whoops. Okay, once again, I want to point out that there's another way that we can do this. Remember the properties of linearity that exist for summations? Because the definition of the definite integral comes from an infinite summation, the properties apply to integrals as well. Now, we will talk in more detail in a later section about properties of integrals, but what I want to point out here is that I could, because there's addition here, I could separate this into 2 different integrals. I could write it as the integral from 0 to 3 of f of x dx plus the integral from 0 to 2 of f of x dx. Okay, and then the integral from 0 to 3 of f of x dx would be a 3 by 1 rectangle. Okay, but then the integral, oh, I'm sorry, not f of x. Back up. That should be a 2. Okay, and this should still be a 3. Apologies. Okay, and then this would just be the graph of y equals 2. Switch colors one more time. Which would be this. And integrating that from 0 to 3 gives us this little 2 by 3 rectangle, which has an area of 6. So we still end up with the same value, 9.